Today's notes are about graphing polar functions. And so now that we've been spending a couple of days plotting polar points, we can plot a bunch of points to generate a polar graph. So we're going to do that by just making a table of points and plotting as we go. Before we get into it, there are some differences between rectangular functions, which is what we've been working in every class up to this point, and polar functions. So rectangular is like y equals f of x. The input and output, input is x, output is y. Examples are like y equals x squared times sine x or f of x equals ln x. Those are rectangular functions, and we can plot them in the xy coordinate system. Polar functions look different. It's not y equals, it's r equals. We still have this function notation. So r is the output, the length of the radius, and theta is the input. And so you'll see differences in the fact that we have thetas instead of x's. Sometimes they might use t here, and it's r of theta instead of f of theta. Right? So 2 sine theta, 3 minus 3 cosine theta. Our polar functions will usually have some sort of trig involved. Okay, so we're not going to rely on transformations or shifting or stretching or any of that. We will always make a table. And even though we plot points r theta, the table that we always make will be picking strategic values for theta, values that make the trig function nice numbers like 1, 1/2, 0, and then plugging that into your function for r. So as we graph polar functions, make sure that you always start, no matter what the polar function is, always start at 0. And then this is another key. These graphs always continue in a counterclockwise fashion. So they spiral. It's like a spirograph. They spiral around and they might do stuff like this. Those are really bad sketches. But as we plot our points, it's a good idea to try to connect the curve a bit as you plot your points so you get in the habit of doing that. When we do some AP classroom problems, it will be important to be able to trace figure out which direction the graph was headed, where did it start and where did it end on a certain interval. Okay, we're going to graph 4 sine theta. This is meant to look like a circle, just a heads up here when we see this format. We're going to let's begin by labeling on this axis where these points are. So the line that bisects quadrant 1, that has to be pi over 4. And then this is pi over 6. And this is pi over 3. Pi over 12 is this mark, and 5 pi over, let's just put this in. Pi over 12 is here, and then 1 pi over 12, 2 pi over 12, 1 pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12, 5 pi over 12 is this one. And then obviously here's pi over 2. Now I'm not going to label around the entire grid, but we can label as we go if we need to add stuff. The other thing I want to do before I start making my table is I like to get in the habit of doing this. What is the trig function that I have? I have sine theta. So let's just plan ahead and say, what are the angles that I should be plugging into sine that generate nice values? So we always start with 0. The sine of 0 is 0. The next nice angle in quadrant 1 is pi over 6 because the sine of pi over 6 is 1/2. So taking half of 4 is going to work out nicely. I don't want to put in pi over 4 or pi over 3 because those values will give me radical answers, and those are not easy to plot without a calculator. So I'm going to skip up to sine of pi over 2. That gives me 1. We always go around the unit circle in order, so the next nice angle would be in quadrant 2 would be sine of 5 pi over 6. That's also equal to positive 1/2. And then I usually finish at pi. So I always plan out for the first half circle, what are the nice angles that I should be plugging in? And then that helps me, I'll need to go beyond that, but that will help me to say, oh, okay, so you're picking the pi over 6 angles, and we will always, for everything, pick the non-quadrant angles to fill in as well. All right, so let's translate this into a little table here. We're picking thetas and we're plugging into r equals 4 times sine theta. So we always start at 0. And so r is equal to 4 times the sine of 0. And actually, let me write this out for our notes. So 4 times the sine of 0, which is equal to 0. So our first point is at the origin, 0, 0. And then the next nice point we plug in should be pi over 6. Remember, that's 4 times the sine of pi over 6, which is 4 times 1 half. So that's 2. So face pi over 6, walk forward 2 units. Now, when you connect these points, we're not getting super accurate. I don't care too much about pi over 12 or anything like that. But you connect this with a smooth curve. So it doesn't have to be a dramatic loop. You don't want it to be too dramatic there. Some people don't like to connect as they go, but you're just curving this a little bit. It's not linear. It's a nice smooth curve. Okay, what else should we plug in? Then we should go to pi over 2. 4 times the sine of pi over 2 is 4 times 1, 4. So we're facing pi over 2 and walking forward 1, 2, 3, 4. Again, this is supposed to look like a circle. If we did plot the radical 2 and the radical 3 over 2, we would get a more rounded out shape. So try to round this so that, like, this is a really bad sketch. So try to round this so that it kind of looks like this. Okay, and then we're going to plug in 5 pi over 6. That's 4 times the sine of 5 pi over 6. That's 4 times 1 half. So you might want to remind yourself, here's 5 pi over 6, this line. So we're walking forward 1, 2. Notice these graphs have symmetry. They always have some sort of symmetry. And then if we plug in pi, we get back to 4 times sine of pi, which is 4 times 0. So we get back to 0. Now, if you keep plugging in points after pi, the graph is just going to trace over itself again. So it's important to know that the graph started at 0, and then remember, these rotate in the counterclockwise direction. This is supposed to look like a circle. This obviously does not look like a circle. I'm not going to be judging you based on that, but if we were looking at like a computer generated graph, it would round out to a much nicer circle. It's something like this is what it's meant to be. Okay, so again, it's important to know that it starts here and it rotates this way as you go around. Okay, same thing for this one. R equals negative 3 cosine theta. This is meant to look like a circle. It's not going to look as nice because we are not plotting all of the decimal values, but we'll just do what we can. So this one's cosine. So let's take a look at this. We always start at 0. Let's pick out our nice values first. Start at 0. Cosine of 0 is not 0, it's 1. And then what makes cosine 1 half? So that should be pi over 3. Cosine of pi over 3 is 1 half. Always plug in the non-quadrant angles. So then you're up at, we've done pi, or now we're up at pi over 2. Cosine of pi over 2 is 0. And then because I picked the pi over 3 angle here, I should be doing cosine of 2 pi over 3. And I'm just trying to remind myself where these angles are. So here's cosine of 2 pi over 3. Now that's not 1 half, that's negative 1 half. Because remember, cosine is negative in quadrant 2. And then let's finish with cosine of pi, which is equal to negative 1. And again, if we need more angles, if our graph doesn't complete itself, if we don't finish where we started and get the full picture, then we just would keep picking angles, but now we know to pick the pi over 3s. So let's put this into a little chart here. This time the equation is negative 3 cosine theta. We always start at 0. Negative 3 cosine of 0 is like negative 3 times 1. So we're going to face 0, which is here, but we're going to walk backward 1, 2, 3 units. So it's important to know that the graph starts here. And then we're going to plug in pi over 3. That's negative 3 times 1 half, which is negative 1 1/2. So we're going to face pi over 3, but we're going to walk, it's easy to lose this line here. We're going to walk backward 1 1/2 units. So you should be on like the 4 pi over 3 line, right? Because that connects up to pi over 3. So we face pi over 3. Now we're walking backwards, so we're on the 4 pi over 3 line, 1 1/2. And then we plug in pi over 2. We get negative 3 times cosine of pi over 2 is 0. So now we're over to the origin, I should say. So far, here's our graph. I'm rounding it out because I know it should look like a circle. All right. And then again, I can kind of, if I realize this graph should look like a circle, I could use symmetry here. and say, oh, on the 2 pi over 3 line, I should be at 1.5. But I can also just plug the number in and see. Plug in 2 pi over 3. You get negative 3 times negative 1/2, which is positive 1.5. So face 2 pi over 3 and go forward 1.5. Again, that point is symmetric to the one that's below it. So this graph continues up and kind of finishes like this. That looks a little more circular than my first one. Not every graph we do is a circle. A lot of the graphs have, if they have more complicated equations, if they have a number with a theta or something being added or subtracted, you'll get a different shape. So let's take a look at our next two examples. This one is 3 plus 2 times cosine theta. Now I want to use the same cosine values. So from the previous one, I'm just going to, you don't have to write this out every time. I'm just going to remind myself here. We want cosine of 0. We want cosine of pi over 3 because that's 1/2. It's going to multiply nicely to 2. Cosine of pi over 2 is 0. And we're also going to want 2 pi over 3. That's equal to negative 1/2. And cosine of pi. Now, when we went to pi in the last graph, that completed the graph. The graph would just keep tracing on itself if you did the next value. Like if I did pi here, I would have had negative 3 times negative 1, face pi and go forward 3. You're right there again. So you would just keep getting the same points. Here, I might need to go past pi if I don't have a complete graph that goes all the way around. So let's take a look at this. So we're picking theta. We're plugging into 3 plus 2 times cosine theta. Always start with 0. That gives me 3 plus 2 times, what's the cosine of 0? 1. 3 plus 2 is 5. Face 0, go forward 1, 2, 3, 4, 5. It's a good idea to plot these points as you go because if you miscalculate something, it won't fall into place in your graph, and that's one way to catch yourself. All right, the next nice angle for cosine is pi over 3. 3 plus 2 times the cosine of pi over 3, which is 1/2. That's 3 plus 1, so 4. So let's see, here's pi over 3. We need to go forward 1, 2, 3, 4. So far the graph, I don't know if I've said this already, but the graph, it's hard to sketch these in the proper order, but this is like a spirograph. The graph will generate from this point, it goes up. Okay, and then what do we put in? Pi over 2. So 3 plus 2 times cosine of pi over 2 is 0. That's 3 plus 0, which is 3. So face pi over 2 and go forward 3. So the graph is now from here going up this way. If you want to make these look nicer, it's always easier to sketch down than it is up. So however you connect the points is up to you, but it's good to know that we started here and we're coming around this way. So now we're going to put in 2 pi over 3. I like to tell myself where that angle is. And then we're going to do 3 plus 2 times cosine of 2 pi over 3 was negative 1/2. So this is like 3 minus 1, which is 2. So face 2 pi over 3 and walk forward 2. So now you're down here. And then we're going to plug in pi. 3 plus 2 times cosine of pi is negative 1. 3 minus 2 is 1. Face pi and go forward 1. So still curving around here. All right, and then I'm out of angles that I've written up here, but now I know it should be all of the pi over 3's that I'm checking. So the next angle is in quadrant 3, 4 pi over 3, which is right here. If we plug that in, we get 3 plus 2 times negative 1/2, right? Because cosine of 4 pi over 3 is negative. So this is like 3 minus 1, which is 2. So notice there's a little bit of symmetry going on here. I'm facing 4 pi over 3 and I'm walking forward 2. So see how this is the same thing we had so far. Once you realize you're going to get a symmetric graph, you're allowed to use symmetry. Like I know the next point, there was a point at pi over 2, 1, 2, 3. There should be a point at 3 pi over 2, 1, 2, 3 to match that. If you're not confident about the symmetry thing, though, you can always plug in points and say, okay, next one would be 3 pi over 2. That's 3 plus 2 times cosine of 3 pi over 2, which is 0. So that is 3. So face 3 pi over 2, go down 3. Plug in 5 pi over 3. 3 plus 2 times, in quadrant 4, cosine of 5 pi over 3 is 1/2. 3 plus 1 is 4. So face 5 pi over 3 and go forward 1, 2, 3, 4. See how that's symmetric though? See how this point, I could have also just gotten that from here. And then if I plug in 2 pi, I'm going to get the same thing I got when I plugged in 0. So I can just connect here. Or again, you can do the math on that. This is called a cardioid. It kind of looks a little bit like a heart, depending on what you get here. Or no, is this a cardioid? Sorry, no, this is a dimpled cardioid. The types don't matter, but if you squint on its side, it kind of looks like a heart, basically. Okay. What about this one? I've changed this. I'm not sure if it's changed in your notes packet, but we just did 2 trig functions with cosine, so I just wanted to switch back to sine. So make this 4 sine of 2 theta before you get started. Now, what does the 2 theta do? So 4 sine of theta was just a circle. The 2 theta makes the graph look a lot more interesting. It's going to turn into what we call is a rose curve. So I still start out the same way by saying, what are the nice angles for sine? Sine of 0 is 0. Sine of pi over 6 is 1/2. Sine of pi over 2 is 1. Sine of 5 pi over 6 is 1/2. And sine of pi is 0. And if I need more than that, I'll keep going. But here's the catch on this one. We're not just plugging in 0, pi over 6, pi over 2, because when you plug that in, you're plugging into 2 theta. So if you plug in pi over 6, for example, it'll be 4 times the sine of 2 pi over 6, which is pi over 3, and that's an ugly number. Okay, so what we need to do is say, well, this is really 2 theta. What theta do I need to plug in to make 2 theta equal to pi over 6? If I divide by 2, I get pi over 12. Now, we do have pi over 12 here. So if this is a nice convenient angle, pi over 12, or sometimes it'll come out to pi over 6 or pi over 4, then use it. If it comes out to something ugly, like pi over 18, pi over 15, something like that, then we're not going to worry too much about that. But this is on our grid, so we're going to go ahead and graph this. What about this one? 2 theta needs to equal pi over 2, so that I get sine of pi, 4 times sine of pi over 2. So divide by 4 and be plugging in pi over 4. This one, 2 theta equals 5 pi over 6. Divide by 2, 5 pi over 12. And again, we have that on this grid, so this is 5 pi over 12. What if 2 theta is supposed to equal pi? Theta is pi over 2. This gives me a good idea of what angles I need to plug in. I need to plug in quadrant 1, 0, pi over 12, pi over 4, 5 pi over 12, and then get to the top. And I'll repeat that throughout. So let's see where we are here. So r is equal to 4 times sine of 2 theta. Always start at 0. 4 times sine of 2 times 0 is still 0. 4 times 0 is 0. So we start at the pole. And then remember, we're plugging in pi over 12. Because when we plug that in, we're going to get 4 times sine of 2 pi over 12, which is pi over 6. And that's 4 times 1/2. So that's 2. Face pi over 12, go forward 2. So here's what we have so far. And then we need to plug in pi over 4. Because when we plug that in, we're going to get 4 times sine of 2 times pi over 4. 2 pi over 4 is pi over 2. That's 4 times 1. So when we face pi over 4, we walk forward 1, 2, 3, 4 units. Now this is going to be the tip of a petal. Like I said, these form rose curves. Take a look down below. This is a rose curve. This is a rose curve. They look like flowers. So when you get the point that reaches out to this leading coefficient here, that's as far as this is going to go, and then it's going to circle back around. So again, you could use symmetry. The next point that's at the next pi over 12 point, the 5 pi over 12, should be at 2. but let's confirm that by plugging it in. So 5 pi over 12, I get 4 times sine of times 2. 2 times 5 pi over 12 is 5 pi over 6. What's the sine of 5 pi over 6? 1/2. So we get 2. So see, we're getting this little symmetry here. So we do get 2. Now this comes back around. And then the last thing to plug in so far is pi over 2. If we plug in pi over 2, 4 times sine of 2 pi over 2 is really just sine of pi, and that brings me back to 0. So here's one petal of the rose curve. Now, this seems like it's going to be really tedious. Are we going to have to go all the way around the unit circle doing this? That answer is no. We're going to rely on symmetry. You could go through and plug everything in, but keep plugging a little bit longer until you get a second petal, and then you can figure out what the pattern is. All right, so let's use the idea of what we did from quadrant 1 to take us into quadrant 2. So we're going to need, what is this pi over 12 angle? So pi over 2 is 6 pi over 12, so this has to be 7 pi over 12. So we're going to plug that in. We also are going to need to plug in 3 pi over 4. And then let's see, 7 pi over 12, 8 pi over 12, 9 pi over 12, 10 pi over 12, 11 pi over 12. I guess I could have done that by saying 1 less than pi, right? So we're going to need to plug in these 3 as our next 3 angles. So let's go with 7 pi over 12. That's 4 times the sine of 2 times 7 pi over 12 is 7 pi over 6. Sine of 7 pi over 6 is negative 1/2. So face 7 pi over 12, which is going to put you on this line, but walk backward 2 units. 1, 2. So now I'm here. So far this graph started at 0, it went around, and now we're down here. Maybe this is enough for you to figure out like, oh, okay, the next petal is down here, and it's symmetric to this one. If that's enough information for you, then go ahead and plot the next 2 points. They're going to be at the pi over 4 angle and the pi over 12 angle. But if you're not there yet, just keep plugging stuff in. So what's 3 pi over 4? 4 times the sine of 2 times 3 pi over 4 is 3 pi over 2. That's 4 times negative 1. It's negative 4. Face 3 pi over 4, walk backwards 1, 2, 3, 4 units. There's the tip of another petal. Maybe that's enough for you to see the symmetry, right? Because remember, on either side of this, the next angle that went out to 2, the other side of the petal, should be on the pi over 12 line. So it should be right here. When I looped that around, I dipped into my... It's hard for me to draw these anyway. It's hard to make them look nice and not like wobbly, whatever. But here are 2 petals. Now these graphs are symmetric, and there's a rule here. So I've got 2 petals here. I can kind of say, oh, okay, so the tip of each petal is in the quadrant at pi over 4. So there's going to be one that goes like in here, 1, 2, 3, 4. Here's the tip of this petal. And in the third quadrant, 1, 2, 3, 4. Here's the tip of this petal, right on the pi over 4 lines. And then the width of each petal was at 2 units out, was on the pi over 12 line. So the one that's closest to each axis is the pi over 12 line. So here's another petal. I'm not connecting them in like the spirograph fashion to generate them properly, but that's okay. So we have the symmetry here. So I kind of stopped here and I used symmetry. And that's okay. I'm actually encouraging that because it's really tedious and you can make mistakes if you plug in a million little angles. Now, it should always work, but you just have to do that carefully. And again, the thing that's important to know is where you started and what was the first petal generated. So we went here, and then where did the graph go? Imagine you're doing one of those spirograph things if you did those as a kid. Then we dipped down here. Oh. And then where would it go? It would go down here and then here, right? Now, sometimes we will be getting questions on like on what section of the curve are you if you're putting in angles between whatever, 7 pi over 4 and 11 pi over 6 or something like that. Now, you can just get those by plotting those points and seeing where the curve is, but it's kind of nice to know which petals were generated in which order. Another thing about these rose curves, here are some rules. You do not have to memorize these. So this is not required to memorize at all. The one rule that I do think is very helpful to have memorized is the thing about the petals. So if it's a rose curve, there are two things to know. It's a rose curve if you have just sine or cosine, nothing is being added or subtracted, and it has a number in front of the angle. If that number is even, if this is even, then you have double the petals. So this is 4 petals. If this were 4 theta, there'd be 8 petals. If it were 10 theta, there'd be 20 petals. That would be crazy. If B is odd, and this is whether it's sine or cosine, then this is the exact number of petals you're going to have. You're going to have 5 petals. The reason for the double thing versus not double, if B is odd, then when you go from 0 to 2 pi, you're not tracing over the same graph twice. But if B is even, you're actually, it should only take you, I think, pi to complete that graph instead of 2 pi. So the 2 pi would like trace over the petals again. All right, what's the other important thing to know? If it's sine always starts in quadrant 1 as the first petal. Like it starts at 0 and then goes into quadrant 1. So this was the first petal generated. If you have cosine always starts on the positive axis and goes around this way. So I know that this graph, without having graphed it, went like this. So cosine starts, let's say, on x-axis. Starts here and goes back to the pole and back through. Every time you go into a different quadrant, you must have passed through the pole or the origin first. I do not have these memorized. I've done polars for years and I just do not have them memorized. They're too similar. I just use a table to graph. We're not going to be given anything to graph by hand, super ornate, or we might not even graph by hand at all. We'll probably be given graphs and have to give information about them. All right, our homework tonight is the graphing worksheet. We just have 4 of these graphs to produce, so take your time, double check them. Come see me if you have questions.